Okay, so Ryan's here. It's 12:30, so let's start. I think this time we set up everything ahead of time, so we can start sharply on time. Today we're really happy to have Professor Anson Hook from University of Maryland to come visiting us and give us a talk on his recent research. Let me give a brief introduction about Anson to people here. Anson graduated from Stanford and then did a postdoc at IIS, then went back to Stanford to do a short one-year postdoc. Then before he joined Maryland to become a faculty there, he recently was tenured. Beyond all those normal history, I think Anson is another example particle physics of our generation, that he has full spectrum. He worked on collider phenomenology in the very beginning, but also do a lot of model building, have very nice work in various directions in astrophysics, cosmology, as well as small scale experiments. But also he have been working on various, have impact in various topics, in particular axion physics. And also he is one of the few youngish physicists who dare to try to think about the hierarchy problem, have his own tricks to help us ameliorate the fine tunings, etc. Okay, but he's still doing some of the research along this line. I believe he will give us some a new twist in this direction. And with that, let's welcome Anson to give for this talk.
So, thanks for the nice introduction. Yeah, so today I'm going to be talking about some work I did with Ricardo last year about sort of an odd feature present in Goldstone bosons, or pseudo-Goldstone bosons. But sort of the context for my talk is, at least, I don't know why everyone else got into physics, but I like physics because I can guess the answer up to order 1 numbers for almost everything. And this is why I really liked physics over mathematics. And in particular, the sort of 0th order trick that you always learn and talk about right away is dimensional analysis, where you can do things like use dimensional analysis to estimate the scale at which something new happens. It might be the floor when you drop something. It might be the electric field at which something happens. Who knows? Sometimes it's the mass of a particle. Sometimes it's a radius. And at least personally, I really believe that dimensional analysis works because it's the one aspect of physics as a theorist that I've tested the most. I've done things like test Newton's law and Einstein and all these things a few times in my life, but I have tested dimensional analysis many, many, many more times. And so despite the fact that there is no theorem that dimensional analysis always has to work, it's just a fact that in every example, dimensional analysis seems to work. Of course, with the standard caveat of you actually have to know the physics, you have to be asking a correct question and all this stuff. But just like Occam's razor and things like that, which are not mathematical facts, as physicists, we know in our bones it's true, even though you can't mathematically rigorously prove it. And so I was hoping for just to start off to give a few examples of dimensional analysis. Some of them you've hopefully seen before, and hopefully I'll give one that people haven't seen before. So they're standard ones. Probably the first one we do is something like drop a ball. You hear some noise a second later, and you say at some distance scale, something must happen. Usually it's the floor. But in this case, you can sort of predict, in this case, it's the distance to your new physics, which is the floor that you apparently didn't know ahead of time. Another fun example is take any sort of capacitor, some charged object, write down the multipole expansion, and try to guess the size of your capacitor, the size of your atom. And this basically, as far as the examples I know of, it always works. And in fact, there's a really fun example, if you haven't done this before, is to do this exercise for methane. Methane is sort of special because it has tetrahedral symmetries. And so actually for methane, the monopole, the dipole, and the quadrupole all vanish due to the tetrahedral symmetry. So if you spin methane, it emits gravitational waves at a suppressed rate. Kind of amusing, but despite all these suppressions, if you start going to higher orders in the multipole, then you will be able to properly estimate or the size of methane. So fun exercise, if you haven't done it before, I'd suggest doing it. Even in the case where I know of where there's the most cancellations possible in the most special case, it still works. Other things you'll see very often, using the classical radius of the electron to sort of guess the size at which something weird happens. You can say this anticipated quantum mechanics. I don't know if that's historically accurate or not, but people post-sticked it. Same thing is true for a quantum example of the same argument, which is go through, use dimensional analysis. People usually decide to draw Feynman diagrams for some reason, but you can do dimensional analysis without having to draw diagrams and guess the sort of charged pion, neutral pion mass difference. And again, I don't think it's true exactly historically that you could anticipate it, but people will say you can post-stick it. The charm quark, they actually did make a prediction using similar arguments. In particular, they sort of just guessed the charm quark mass, and they didn't get it exactly right, but they got some bound on it. The one I actually learned most recently that I thought was really fun is back in 1922, Fermi predicted the existence of stimulated Schwinger pair production. And this, you'll notice, is before the discovery of the positron. So he did not know, he used dimensional analysis to predict a scale and said, I have absolutely no idea what happens at this scale, but I think something does. And so how did this argument work? Oh, and he did this as a graduate student. And so if you're a graduate student in the audience, this is what you have to live up to. I've already passed my prime, I can't do this. But as a student, maybe you can. So what was his argument? He took an electron and you shoot it in a magnetic field. Everyone knows an electron in a magnetic field goes in circles, right? Standard stuff. And let's calculate the Larmor radiation from this guy. In particular, it'll emit photons, and it has to be quantized in sort of units of your oscillation frequency. And go through, calculate the relativistic version of Larmor, your Larmor frequency, and you get some number, gamma squared EB over M. And what Fermi said was, well, this would be really weird if this was larger than the total energy of the electron, right? Gamma times M. So what he said was, when these two guys are comparable, something happens. He had no idea what happens. And so that's basically gamma EB, or the effective electric field observed by the electron is of order M squared.
What is gamma? It's a number.
It's the energy of the Lorentz boost of the electron.
Okay.
Yeah, sorry. And so the boosted B field is in some sense the effective electric field it's saying. And so he said something has to happen when it's of order M squared. I don't know what. He didn't know that what actually happens is this guy will emit a photon that then splits into E plus E minus pairs. So stimulated Schwinger pair production. And positron was not discovered, so he couldn't actually say what happened. He couldn't calculate it. He just said it would be quite weird if nothing happened. So I think something happens at the B field. And in fact, you go through and calculate this, and that's exactly what you find. It's a fun point of fact that this was actually calculated by astrophysicists because they were interested around neutron stars where there are huge B fields and electrons flying around. And so they actually, depending on which astrophysicist you ask, they would say we have observed this effect and it's critical for how neutron stars work, or other people are a little more curmudgeon-y and will say, well, who knows? But either way, I found it amusing that this was sort of stuff done that you might think should have been done by particle physicists, but was done by astrophysicists. Oh, and amusingly, this example I gave of methane, all the group theory involving the multipole here were done by chemists, and not by particle physicists or mathematicians or anything. So amusing.
Can you have more calculations? Like, is it the maximum?
So what chemists have proved is that every discrete symmetry you can do. So actually, you can brute force the problem because this is just three-dimensional space, so subgroups of SO3. You can brute force it and write down every single discrete symmetry group. and then find that every single one can cancel up to the quadruple, but nothing else. So it's a brute force thing you can do. If you decide to live in higher dimensions, I'm not quite sure. But it goes back to this sort of folk theorem, which is just if you have non-abelian groups, you can't have discrete subgroups that tile it perfectly. The best you can do is a Zn subgroup of a U1, so the abelian part you can do quite well, but you can't do it for non-abelian. Okay, where was I? Okay, so great, dimensional analysis is pretty awesome when you use it correctly. So as Jen said, there's a bit of an elephant in the room whenever you say these things, which is depending on who you ask, sometimes people will say, oh, I'm using dimensional analysis, something or another, some other version of it. Sometimes people even say they know the order 1 number. Like I say, this is dimensional analysis for me, so I'm not entirely sure you know the order 1 numbers. But they say there's something happens at 500 GeV. And so what do people say? Well, first people said that must be the mass of colored particles. For example, that's what happens in supersymmetry. Then eventually people were like, well, actually in extra dimensions and more complicated, like little Higgs type theories, what happens are actually it's colored scalar fermions rather than colored scalars. Then people got more and more inventive and wrote theories where what happens there is uncolored particles, just particles in general. And so if you subscribe to this philosophy, then you're going to be very confused because where the heck are these 500 GeV particles? I would have just said, well, you just didn't predict order 1 numbers right, because it's not like we go that far beyond this 500 GeV scale. But if let's just say there are no new particles at this scale, if you believe you're asking the right question, then we must be missing something important, right?
Yeah. Did you get this number 500 GeV from the radiative correction to the Higgs particle?
Yeah, so that's the argument they use to say that they know the order 1 numbers.
Yeah.
I would say I have plenty of counter examples where you don't test the order 1 number are correct, but they really believe that they have the order 1 number, right?
I'm sorry to interrupt, but I mean, because of my age, I remember the beginning of this. So at the beginning, nobody was thinking about 100 GeV for Higgs. People were implied that Higgs would be like 10 GeV. So in this way, the shift to higher numbers was experimental rather than theoretical.
Yeah.
So in this way, this argument that it is 500, has no meaning.
Yeah. So this, when you're estimating the scale, this 500 Higgs, observed Higgs mass is input.
So, no, but if you put 10 GeV for Higgs mass, then it would be not 500, right?
Yeah.
And people did not think about 500 GeV at the beginning.
Mm-hmm. Yeah.
So in this way, it's okay. It's you can argue about Higgs curl, which is 200 GeV, right? This would be the valid argument. Reference to the Higgs mass is not valid argument.
Mm-hmm. Yeah. So I guess the approach I'm going to take is I'm just going to say people say this, and rather than argue philosophy with them, I'm going to provide a counterexample. I find if you disagree with someone, a counterexample works much better than arguing philosophy with them.
No, but counterexample to non-existing example is not a counterexample.
Well, I think the statement is people will claim, given the observed Higgs mass, given the observed everything, that there needs to be particles at a scale that are parametrically of order M Higgs over the Yukawa coupling. So this is
right. In this argument, you can take Higgs mass to be, say, 1 GeV. Why not?
Yeah, that's fine.
All right. So what is the argument then?
I mean, the argument is basically like saying, estimating taking two terms in the multiple expansion, in this case, the Yukawa coupling and the Higgs mass, and trying to estimate the size of the Higgs boson. right? Just like you have a capacitor.
No, yeah, Higgs boson, we are now experimentally, but the theory does not predict mass of Higgs boson.
That's right.
So the only masses you have in mind kind of predicted or whatever it's.
I'll say the following, which is people will say, if the Higgs mass is not calculable, then you're asking the wrong question here. When you do this dimensional analysis, you can get the wrong answer if you ask the wrong question. And if the Higgs mass is not calculable, this dimensional analysis argument is just wrong because you asked the wrong question. What I'm going to do is give a theory where the Higgs mass is calculable, and this is still wrong.
I see. Yeah. Okay.
And so I'm going to try to live up to all the caveats that everyone says, and then still say no particles at this scale that they numerically predict. Yeah. So, okay. So, yeah, like I said, I'm here to make friends with all the people who say this by providing a counterexample to everything. And so the idea is basically going to be, I'm going to write down a theory where the Higgs mass is calculable, but the new particles are parametrically further away. And in particular, this dimensional analysis argument is still correct, but it's not predicting the mass scale of new particles or anything like that. If you did some collider or whatever in this hypothetical world, you would not find new particles at the scale where people say. Okay, so let's just go through this. I'm gonna first just write the IR effective field theory, which has this property. I'll briefly discuss the UV completion just to show that we aren't tricking ourselves or anything. The IR EFT will have convergent integrals and everything will be finite. So you might not say you even need the UV theory. Finally, I'm gonna sort of talk about a bit about interpretation. I will admit, we don't fully understand why the results are the way they are, other than just we can calculate it, show that everything is finite. And then, yeah, okay. So the basic statement I'm going to make is if you have the normal Yukawa coupled theory, you'd say, oh, the effective potential for phi is UV divergent, it requires counter terms, et cetera, et cetera. The claim is, I'll sort of justify this potential a little bit more, but if you take a pseudo-Goldstone boson, so in other words, a periodic scalar of some sort, and you write a periodic coupling to some fermions, that at low energies would look very much like this, sort of the quadratic divergence or dependent things, is if you calculate the effective potential of this non-renormalizable theory, this pseudo-Goldstone boson theory, you will find that at the y squared level, there are no divergences in the effective potential of phi. The mass is finite, the coordinate coupling is finite, et cetera. Everything is finite. Again, I won't say I know why, other than I'm going to do the calculation and I'll see this is the case.
But this means that there is a symmetry here. It's hidden. It's non-linear.
Yes, that's non-linearly realized. So if you decide, in particular, you don't see the periodicity of your angular fields phi here. If you look just at the lowest order term, you actually have to see the full periodic symmetry of this thing.
No, but just a moment. They suggested Lagrangian is much more divergent than the first one.
Yes, and despite this, at the y squared level, it'll be convergent.
No, it's not an argument. This Lagrangian contains much more new divergences than the one which is linear in phi.
Yes, that's right. And in particular,
so in this way you are saying, let's go get all these divergences to get rid of just the first one.
So the statement is, this is a non-renormalizable theory. There are going to be an infinite number of divergences. But if you look at just the y squared level and just the effective potential of phi, it'll be finite. So that sum of the entire theory ends up being finite. So like the cosmological
but it is an assumption. It's not a statement.
No, I can calculate loops here and calculate and show that there are no divergences.
No. Just a moment. So you are saying that the theory is renormalizable, but I mean, naively, it looks like completely not renormalizable.
Oh, no, I'm saying it is non-renormalizable, but I'm just saying at the y squared level and just the effective potential of phi, there are no divergences. At the y to the fourth level, there will be divergences. If I don't look at the effective
No. But this is this could be kind of trivial. Like, say, for example, this Lagrangian is, say, or for example, that there are some discrete symmetry which does not allow phi squared term, for example, but does allow phi cubed term or whatever, right? So this does not
sine squared. Here.
Okay, no, and okay, but it does not cure the series. The series still sick theory. Even if this, if particular term are suppressed by certain, for example, discrete symmetry, it does not help you to state that the series does make sense.
I mean, non-renormalizable theories make sense, right? This is a non-renormalizable theory is the multipole expansion. We use it all the time. The standard model is non-renormalizable. It involves like neutrino masses and things like that. Still calculates things to 10 orders of magnitude precision.
Like, no, I do not understand. A standard model is renormalizable.
Not with neutrino masses. If you just write down the HL squared term,
okay,
masses.
Okay, but then it's not a standard model.
Yeah, but I mean, the standard model is excluded, right? You've measured neutrino masses.
Yeah, but
No. Just a moment. I am talking about particular statement. When you are saying the standard model is non-renormalizable, this statement is untrue.
Okay, it's also excluded because you don't want to talk about neutrino masses then. So
okay, then it's not a standard model. Then it is a model which you can discuss, which is not a kind of extension of standard model or whatever, but not a standard model per se.
Okay, fine. I'm just saying standard model with neutrino masses, which corresponds to reality.
No. I do not accept this. Standard model with non-renormalizable addition is not a standard model.
Okay, fine. We can just say some technicalities there about how you choose to define the standard model versus me.
Okay, so what? By itself, it doesn't prove anything. Okay, you can discuss non-renormalizable theory by itself is not a big deal because you can believe that you fix the theory at certain scale and then calculate it further, and the theory is non-renormalizable. But doesn't if you put particular way of fixing operator coefficient in Lagrangian at certain point, you can calculate what would be in infrared. So by itself, the problem is that the number of parameters you are fixing is infinite.
Yeah. Okay. So how about this? My claim is in this sine phi theory, you calculate the corrections to the mass at the y squared level, and you do not need a counter term. That's a concrete statement. Right.
No, then you can discuss why in this particular example phi squared term is suppressed because generically the theory is not renormalizable, and why particular phi squared term is not there. I mean, it is up to you to find explanation of this.
Yeah, but I'm just going to say I'm going to calculate it and show that it's the case.
It's not an explanation.
Yes.
Because if you believe that there is a certain principle which governs absence of phi squared term, then you should pronounce this principle.
Yes, and I say I don't know this principle.
Okay, then it's just observation with which kind of still hanging on.
Yes, that's right.
Okay. No, it's okay. No, I don't mind that, but I would say that you are putting the question, you are not giving an answer.
That's right. This claim is I tried very hard and I could not come up with an answer.
I see.
Okay. Hard. I mean, neither of us could come up with an answer. And we're hoping others who are smarter than us can figure out the answer.
No. You should prove that you are smart yourself.
I wish I was. Okay. So let's actually just do this calculation. First, let's just very briefly just say how I can force this coupling by symmetries if you want to. First is you can just say there's a shift symmetry under which the Yukawa coupling transforms to the spurion, so that the only invariant combination of for your PNGB is some combination of your Yukawa coupling times phi. In other words, some sine and cosines. And then if you apply a Z2 symmetry, you can force the sine or cosine to be a sine. So the statement is, you can, if you take y very, very small, this will be your leading order coupling you can write down that couples things together. And so now let's just calculate corrections to this theory. So since the way I'm going to do it might be a little, some like students might not have seen before, let's do a warm-up question just to show what the techniques I'm going to be using are. So what I'm going to do is calculate, given some regularization scheme, what would the IR experimentalists observe as the Yukawa coupling between the scalar and the fermion? Right. So in particular, there are loop order corrections at order y. And so let's just calculate these. So first, you can expand well. There's a sine cubed term. So a correction to the Yukawa coupling could come from here. I'm not going to bother to actually do this integral since it's, again, regulator dependent. But again, I want to just illustrate the technique. You get a minus sign from two derivatives of the sine. You get some symmetry factors, you get some coupling constant, and you get a loop integral. And I'm going to be working in position space rather than momentum space. So right, people are probably much more used to working in momentum space, but in position space, this is just the minus sign again, the symmetry factor, coupling constant, and then the propagator of scalar going from 0 to 0, right? Going back to itself. So it actually looks a lot nicer in position space. You can then say, okay, great. Let's do something weird and let's calculate the two loop correction. It turns out, right, you sine, there's a fifth order term. There's some more cyclical symmetry factors involving exchanging the loops. And then there's just the loop thing squared. And then you can continue to do it. Do 3 loops, 4 loops, 5 loops. And basically you get the loop factor to the nth over 1 over n factorial symmetry factor. So that if you add these all corrections together, you would get a correction to your effective potential or your Yukawa coupling that basically just exponentiates the one loop result.
And why you believe that the function would be still sine phi divided by 2f? It could be a different function.
Because it's periodic, right? So the symmetry.
Okay, but a sine cube is also periodic.
Yes, and so but sine. Notice every sine appears with a y. So the sine cubed would be y cubed, and I'm forcing myself to work with only y to the 1 power right now.
Why do you take into account only tadpole graphs? Because in principle, in this theory, there are quadratically divergent graphs with fermion, like fermion.
And I will be doing those next.
Okay.
The only point of doing this is to introduce a different way of calculating it, which is how I'm actually going to be doing those diagrams you mentioned.
No, but if you look at your result, then you're saying that the result is 0, right?
Yeah. So for example, if you did dim reg, this loop here is 0, and you just say whatever I wrote in my Lagrangian at the order y level is what you observe. If you decide to use UV cutoff, then I think I wrote it on the next thing. Decide to use UV cutoff, you see some exponential whatever. But I don't care about any of this stuff actually, other than the top line here, which is just leaving it in terms of I haven't actually done the integral yet. And so that's actually all I care about is this top one here. And actually, in some point, all I care about is the fact that this is the end result. And I'm now going to calculate it a different way using the path integral, which turns out to be like basically a one-liner way of doing these calculations. So in the end, all I want is to compare this to a path integral calculation of doing the exact same thing. that turns out to be much faster. And so I don't have to make sure I get combinatorics factors right and all that stuff. Like when things exponentiate, usually there's some easy way to do it and see it, rather than doing the stupid brute force calculating lots and lots of loop diagrams. And
Sorry, Anson.
Yeah.
What does the position space equal benefit? I couldn't do that.
It'll, that's right. Yeah, that's right. When you do it in the one that was mentioned just earlier, the fermion loop, it'll be much more, you need it in position space, not momentum space.
Just in this example, there's no advantage.
In this example, there's no advantage. And all the point is to introduce the path integral way of doing these results rather than anything else. Yeah.
Normally there's one fewer interval to do.
No. No.
It's going to be a lot more than one fewer for the diagram.
No, but essentially, you're proving that that it is kind of Goldstone boson instead of Yukawa interaction, because you're saying that there is no Yukawa interaction is suppressed by the way you are doing this. But I mean, if you introduce a finite cutoff, for example, then the result would be something non-zero, and it could be anything.
Yeah, that's right. It could be anything.
Yeah, right. So in this way, when you're saying suppression, it in this kind of conditional sense.
Yeah, that's right. So that's why I said when I wrote this thing, I actually don't really care about this bottom part. I only care about the top result. You could even just say, I do dim reg. I don't care about this, anything else. And then my result is kind of trivial.
No. You are saying more than that. You are saying that you cover that the way you treat this power diversions. You are saying that this self kind of suppressing stuff, which doesn't allow Yukawa coupling to be present. There is no Yukawa coupling.
Well, I mean, I have a finite cutoff, right? I'm not taking the cutoff to infinity or anything like that. Since this is at the end a non-renormalizable theory, there's going to be new stuff wrong.
Okay, and what is this cutoff? Where you would stop? Because you're integrating, and you should say that you have an upper limit and lower limit, right?
Yeah.
Or I mean, some normalization point, right?
So calculate the unitarity bound coming from the Lagrangian I wrote. It'll be something, and in fact, I'll write down what it is later, and then put that into here, and just say the highest it could be.
Okay. Yeah. No. Then in this sense, you are saying that the theory cutoff itself in this particular mechanism, okay, and it is what it gives you a meaning of this lambda, right? When you put it. Okay, no, I right, but I would say that it is still very close to saying that there is no Yukawa coupling.
Yes. Okay. So let's just discuss how to do the calculation we just did using a path integral. In particular, all these diagrams come about from doing a path integral and then doing a Taylor series, right? This is how we normally do things. And if you just write down what is the path integral we're doing, there's the sine piece, the sine e to the I phi over 2f, that's the sine, plus the Hermitian conjugate, which is how I get the sine. There's psi bar psi, there's the Yukawa coupling. And everything I got before was from Taylor expanding this exponential here, right? However, you'll notice this is an exponential, and it looks exactly like a source term for phi, right? It's something times your field phi. So this looks like some delta function source term. And if you do Gaussian integrals with source terms, this is one of the first path integrals everyone learns to do in quantum field theory. So this path integral is actually something quite easy to do. You complete the square. You see, right? You complete the square. And here, your source terms are delta functions of where I put my insertion. Now, both of these are now, this basically sets x equals y equals wherever the location is. X minus y gives 0. And so you get exactly the result we had before. Right, so this exponential just comes about from doing the path integral very easily without having to do anything special. Okay,
But when
No, but look, you will talk with the people who doing dimensional regularization, and they would say to you that none of this is present.
Sorry, UN.
No, because people who are doing dimensional regularization insist that in dimensional regularization there is no power divergence. Remember?
Right. Yes. And so in the end,
it's not that I agree with them, but I'm just trying to remind you.
Yes, and which is why when I go next and calculate loops involving fermions, I'll get something that is regulator independent. So here, the whole point of this was just to say, show people path integral is easy, and do things in path integrals, don't do Feynman diagrams.
But it was made easy because of your choice of interaction.
Yes,
Sign.
this is pseudo Goldstone bosons.
Yeah.
Actually, pseudo Goldstone bosons of U1s are simple.
Yeah.
If this was not a U1 PNGB, it would be a lot more harder. It wouldn't exponentiate quite as well. Yeah.
No, but if it's but look, if it's pseudo Goldstone boson, you would say that the vertex, this Yukawa vertex, is not allowed.
Well, the pseudo part is doing all the hard work, which is it's not exactly a Goldstone.
No. But I mean that essentially you're proving in the limit of large cutoff, you're proving that it is not pseudo, it's just kind of Goldstone boson because there is no Yukawa count.
Yeah, or exponentially small.
Yeah.
So I guess I just wanted to make it clear. Here I am doing a Taylor series in Y. And so that's why Y is not in the exponential with the rest of the action. And so this result is only linear in Y. Okay. So let's go through and do diagrams of this sort, which are contributions to the effective potential of phi that are order Y squared. So loops by themselves on either end, across. We're just going to do every single one together all at once. So what you do the path integral again, Taylor series in Y squared. This fermion piece here gives you the standard trace. Okay, so it's in position space, so slightly less familiar to some people, perhaps. What you do though, so that's the fermion piece. You have the scalar piece, which is, again, you do some background field type approach. You Taylor series it, and you'll notice that Taylor seriesing sine squared has pieces, let's say, that are cross terms, which actually depend on phi 0, and pieces that do not depend on phi 0. So we're going to care only about the effective potential for phi. So it needs to have some phi 0 dependence here. So that's a cross term. And in other words, sine squared has a cosine in it. I'm taking the cosine. And so what is that cosine piece? There's, well, it's plus Hermitian conjugate is how you get the cosine. But again, now I have two insertions. One to the left at minus x over 2, and one to the right at plus x over 2. These are the two sources. And so doing every single loop integral possible is just doing the exact same Gaussian integral now with two sources instead of one. Big whoop. We can do that still. We can still complete the square. Oh, J is 2 delta functions now. Plug it in. And what do you see? There's a piece which is proportional to the propagator of 0, which is these loop diagrams here, which go back to itself. There are there are pieces that stretch from one to the other, which are propagators going x or minus x. Okay, so what does this piece do? You'll notice this piece, the D0, the propagator of 0 combines with my y here to give exactly my observed value. That is independent of how I choose to regulate everything. So I'm going to write my answer in terms of physically observed values, such as the observed Yukawa coupling, which has this self propagator too. I have these guys here. And what it notice is a propagator of a scalar is 1 over x squared. And so here, this rest of this thing just dresses my integral like 1 over x squared. So in other words, the result of all of this is my integral of position, dx squared over x to the fourth, which has things, let's say, like a quadratic divergence and everything. But you'll notice it's dressed now by an exponential e to the minus 1 over x squared. In other words, if you Taylor series this exponential, you'll get a quadratic divergence, you'll get a chordate divergence, you'll get all these divergences. But if you actually don't do the bad thing of Taylor seriesing and just do the integral, you get a finite answer.
No, but it is the same story, because if you do it order by, say, one fermionic loop, okay, then you take just one fermionic loop, you will get square of your sign, right? Square, and multiplied by quadratic divergent coefficient, right?
Yep.
And no, it doesn't it's not in contradiction with what you wrote, right? Because you will,
yeah,
if
that's
you
right. But
in what you expected, but no, how to say, this implying that summation goes exactly the way you are writing, neglecting all other divergent part which are present there, including divergent part for self-interaction of phi. I mean, I would call it rather assumptions than the statement, because you are saying, the theory cut off itself. Okay.
yeah,
So it could be in the way you are doing this. I agree, but to say that I would believe it, no, I would not buy it.
yeah. So the statement is the theory cuts itself off, and if this scale f is smaller than my UV cutoff, which turns out to be possible to do, then it cuts itself off well before the UV cutoff, where the theory becomes strongly coupled.
No, but it is certain scale. The scale is given by f or whatever. You do have a scale, right?
Yes, I do have a scale, which is the periodicity of your scalar phi. Yes.
Yeah, right. So in this sense, this scale could be larger than cutoff or smaller than cutoff. It's up to you.
Yeah, and the claim is if it's smaller than the cutoff, I have this theory gives a finite correction to the effective potential without having new particles, new anythings. I don't have to go to supersymmetry. The mass is finite without having to add new particles, the cost of which is to have new interactions and things like that.
But it is only for the certain sequence of diagram you prove, and you did not include, say, for example, the power diversions associated with self-interaction of phi. They are not there.
Yes, they are higher order in Y.
Yeah, right. I agree, right.
And that's why I said there is no divergence only at the Y squared level.
Yeah, no, I got it. Yeah.
Divergence is all over the place.
No, but okay, but then in principle you can go further in Y, in powers of Y, and look whether these extra terms are larger or smaller than the one you calculated, right?
Yes, but if I take Y small enough,
right? I see.
And so I'm not saying Y of order the top Yukawa or even the up Yukawa is small enough.
No, but look, when you allow this kind of power diversions, then however Y is small, you can compensate the smallness by taking cutoff larger.
Yes.
But technically, I agree with what you say.
Yeah. At this point, I'm just saying here are technical statements.
Yeah.
And in terms of how best to use it, I'm not entirely sure. It's just amusing that this is a non-renormalizable theory that in this subsector or at this level seems to cut itself off. It does not cut itself off if you calculate the cosmological constant or if you calculate phi or higher order in Y.
Was the first order in Y, and did you get a quadratic divergence? Y to the 4?
Yes, that's right. And
but there's a symmetry reason. Q1.
Yeah, so there is a shift symmetry which forces the structure. I don't know if I'd call it a reason until I actually understand it and can do it without a calculation. If I could just say, right, this is what was being complained about earlier, which is I can do the calculation, I can't really understand or prove it without a calculation. which is how you actually say you understand it. Right. Yeah. Okay. So the final result comes from basically resumming diagrams of this sort. You get a loop, one guy, two guys, three guys, four guys, and they all come from Taylor expanding this exponential, which you'll notice has a radius of convergence of 0. So yeah, you do a Taylor series about it, you're not going to get particularly sensible answers. And your intermediate result, you actually have to do the correct calculation from the very beginning. Right? This thing has an essential singularity at x equals 0. And so trying to do any Taylor series or anything like that, you just get the wrong answer. Or another way of saying this Taylor series is not commute with this exponential integral.
Yeah. In some sense, if you work backwards, you constructed a theory which is finite, y squared.
Yeah.
Can you?
But your statement that effective y would be still 0 remains, or it doesn't?
See what that looks like.
I haven't been able to do that. And I guess my hope is if I understood why this happens in more detail, then maybe that would make that a lot easier.
Well, I was thinking actually the other way around. If you
just
do the
actually
construction to y⁴ level and compare the two, you might be able to understand
the reasoning better. Yeah, that's possible.
That might
yeah.
be easy.
It might be easier. So yeah, I don't know actually. I haven't tried it. It's a good idea.
But let return back to this first order in y. This statement that effective y goes to 0, which large cutoff, it is still there, or it's not?
Here, we can't.
Oh, you can't hear. Oh. Okay, 1 second. It seems there are multiple questions coming up at a time.
Okay, I'm sorry.
That go back to you in 1 second. What happened?
Yep, I can change.
Anyway,
I was just gonna ask, like, why doesn't this happen at the y⁴ level? Like, the y⁴ fraction still have to
this minus sign appears to be an accident.
like it flips sign.
Flip sign, and so then it just becomes more divergent.
Okay.
Like I said, I lack understanding of exactly why this behavior happens.
But does the y⁴ contribution still have some shift symmetry to it? Like maybe
Yeah,
it has
that's
like
right.
that last
It
term.
goes as cosine squared instead of cosine
Okay.
at the y⁴.
So with this,
Sorry, go ahead.
yeah, excuse me, with this exponential factor, you in principle lose the ability to rotate to do weak rotation from Minkowski to Euclidean, right? Because exponent e to the power minus x squared has a very bad analytical properties. It has essential singularity if you go around.
Yeah.
So this kind of, I'm a little bit concerned about that.
Mm-hmm. And yeah,
But-
not actually sure. So actually, one way you can see that you're going to get something with an essential singularity is if you start off with a periodic scalar, you have sine and cosines, and then you have f, and you'll notice this has this function just has an essential singularity at f equals 0, right?
Yes.
By dimensional analysis, every place in here that f appears, x also appears. And essential singularity in f means essential singularity in x. And so somehow this, I guess what you're saying is that because you have any periodic scalar always has these weird exponentials, they hit essential singularities, and maybe that screws up some analytic continuation. I haven't thought about it at all, so I can't.
No, but I believe what is written is already written in Euclidean space.
What I was going to say is that if you know that the origin here of the finiteness being due to the shift symmetry at this level, you can, I suppose you can ask the question at least, what symmetry would you need to enforce it at the next order?
Yeah, that's right.
And then work it that way.
Mm-hmm.
But Anson, but I was trying to return to the beginning. In the first order in Y, you were proving that effective Y goes to 0, right?
Yeah. If the UV
It is still there, right?
yeah.
So in this way, all these finite terms are about squaring of the quantity which was already suppressed.
Yeah. So I sort of secretly hid that into this observed Yukawa coupling.
Yeah, no, it's what I'm
Yeah.
checking, right? So in this sense, I mean, I certainly agree that along this line, and you can do it in not in X representation, or you can do it in momentum space. You still can reproduce what you wrote, right? This particular thing. So I do not think that there is any kind of technical issue with deriving this exponential form, but to me it's still not convincing in terms of what interpretation. What does it mean?
So what it might mean is, let's say I'm an experimentalist that lives in the world where, where sort of all that thing does this corrections here. I would, let's say, measure the Yukawa coupling. I would measure the mass that comes from this guy. And if I decide to do the argument that everyone else likes to do a lot, and they would discover that new particles are at the scale F, and instead, they would be wrong. What happens at the new scale F is indeed, there are some modifications that appear in this exponential, but it's not new particles.
No, but you will measure a new scattering amplitude for phi, right?
That's right. So what instead the new things you would see is, well, this two-loop guy is becoming important. You'll so discover like, oh, I should actually be emitting an extra phi, or maybe 2 phis instead of 1.
Right.
There are physical effects, 100%. They are just not new particles, or not a resonance, a little bump hunt that you should be doing.
No. But it is then it is again back to this kind of symmetry which maintains this form of potential, because like for example, if you would dealing with kind of sigma model in 2 dimension, then you have a symmetry which maintains particular form of Lagrangian. Okay, it's not about immersibility or non-immersibility. It's just that the form of Lagrangian is kept by symmetry, right? By global symmetry.
Yeah, that's right.
And you're close to this, right? Because you are saying that kind of this sign potential has no correction or small correction.
Yeah, that's right.
Right, but we do not see the symmetry, right? You did not formulate it, so that's why I am asking.
And so, yes.
Very good question. So you say like in Y to the 4th you get bouncing to the minus. So how about Y to the 6th, like Tuesday?
I think at higher orders you always see both. Some pieces have the plus, some pieces have the minus.
Okay, so only really only plus.
Yeah. It might be, like was said, it might be possible if I was just sat down and tried to do it a different way, I could just actually force the cancellations at Y to the 4th too. Using different symmetry, I'm not sure. Yeah.
What is the UV cutoff for this theory?
Excellent. Unitarity bound. Let's just calculate the unitarity bound on some periodic scalar. And the main thing, you know the UV cutoff has to depend on Y. If Y was 0, this theory is a free scalar, free Fermi. How does it depend on Y? Turns out you go through end-to-end scattering with a fermion on either side. Turns out this is the best looking thing. And depending on your energy, a different end is the best thing to do. You go through, you calculate the matrix element of this. Looks like this guy here. Requiring it to be less than 1 means that basically the UV cutoff here, or the energy per particle, has to be less than 4 pi f log Y. So it's actually logarithmic in the Yukawa coupling. So it doesn't become large very quickly as you take y small. In other words, if you want to parametrically separate the UV cutoff from 4 pi f, then you need an exponentially small U column.
No, but you have you can increase number of particle n, and then your limit could be infinitely large.
No, as n the n factorial in the denominator here eventually is more important than the e to the 2n in the numerator. So if you actually
but look at your limitation. Square root of s divided by n, right?
Yeah.
So it means that if I'm increasing n, the square root of s grows as first power of n.
Oh, yes, that's right.
No, and in this sense, it would be infinite.
Yeah, that's right.
But if you take n of order 1,
Yeah.
let's say 5 or 4,
Mm-hmm.
then what happens? Then you have power dependence on y, right?
Yes, that's right. Because it's, as you can imagine, as you slowly increase the energy, first it's the 1 over f piece, and then it's 1 over f cubed, well, then 1 over f to the 5th, and 1 over f to the 6th.
Yes.
And so as you slowly step up, a different guy comes in every level to become important. And
No, but unitarity is sufficient to violate unitarity in any amplitude, not necessarily some particular chosen.
yes,
Let's
that's
take
right.
you consider 3 into 3 or 4 into 2 scattered.
Yep.
2 into 4. If you saturate the unitary limit at this amplitude, that's also a valid limitation
Yeah,
on
and
y,
so
right?
yes. So in other words, you have to maximize over n, find the strongest constraint, and then choose that.
No, but look, the second constraint would be in when a number of particle grows, the constraint would be kind of going for larger and larger, right?
Yes.
Yeah, so which you are saying that you are choosing square root of s for n over the 1, or this
I'm
constraint?
saying if you take an arbitrary n-to-n process, you can actually generalize n-to-n, the fermion on either side, all this stuff. You get an expression at the bottom right here, which is the matrix element. And then you can say, I want every single one of these to be smaller than 1. Not just for n equals 5, n equals 10. I want every single one. And if I impose that constraint, it turns out to be, at least in the large n limit, equivalent to the
I see. Okay. So then then it means that for very large n, your square root of s would be much larger, right?
Yes.
But then should you apply this larger square root of s for any process with smaller n, or is the other way around? You see that, because you can say, you stop at square root of s not proportional to n, right? Just stop at 4 pi f.
Yes.
Okay, and it would be certainly it would make all amplitude unitary bound would be not broken anywhere, right? It's what Misha says.
Yeah, so I think I might have it somewhere. Did I do it? Yeah, so if you actually ask for a given energy, what n maximizes the unitarity bound, it scales as your energy over 4 pi f to the 2/3 power. So as you go to higher and higher energy, which n dominates, it will change.
No. I think it's not a correct way to go, because if you say that 2 to 2 amplitude gives you limit 4 pi f, right? For a square, no, I mean not counting log of y. 2 to 2, yeah.
If I say I'm scattering with, let's say, 8 pi f instead of 4 pi f.
Okay, yeah, okay, for 8 pi f. But then, even for the process with large number of particles, you still should put this limit which you took from you know, this two amplitude, not invent every time new upper limit, because you can say, aha, you believe that you have a kind of cutoff which is universal cutoff for any number of particles, right?
Yeah.
No, I mean, because otherwise you are saying that your cutoff depends on number of particles, but
Well, I'm saying energy per particle is should be less than something, right? If I'm just taking 50 particles, the energy per particle has to be less than some number.
No, I disagree. Right? No, I disagree. I would say that that once you took this cutoff from 2 to 2 and put it for a larger number of particles, then the amplitude with large number of particles would be smaller and smaller because it will be suppressed by n.
Yeah.
You see,
saying this
you see, because you cut off your integration earlier than you need to cut off, right?
Yeah.
No, because but if you believe that it's universal cutoff, then it means that many particles amplitude should be cut off earlier, and then I think it does contradict to your way of calculation, right? Because when you're summing up all this stuff, I'm not sure. Maybe it doesn't contradict. I'm not sure. You see that in this way, when you did this calculation, you imply the same cutoff everywhere. You didn't invent cutoff dependent on number of particles when you sum up this loop diagram.
Yeah, that's right. I think S over n, so the energy per particle, is less than 4 pi f log. That is not an n-dependent statement, right? I'm just saying every particle you throw at each other has to have energy less than 4 pi f log y.
Okay,
if you do that, then it doesn't matter. You will be okay.
Yeah, I see. Okay, so in this way, number of loops is not important. Then in each loop, you are limiting yourself by this particular energy, right?
Yes, that's right.
Mm-hmm.
Okay. Let's see, where was I? Okay, so another way of saying this is that the experimental consequence of this is the number of particles that are important for any given process, like some scattering process like I just did, grows with energy. So this is the physical effect that happens when your energy reaches 4 pi f, sort of, as Sakati basically said this earlier. Okay, let's skip this. Okay, I'm running over time. So should I even talk about the UV completion?
Yeah.
Yeah. Okay. So let's write down a theory where the UV, where you're like, I have F. Shouldn't the UV cutoff always be 4 pi F? How can I even make it possible go beyond that? And so let's just go through an example. So starting point for every PNGB is spontaneously breaking a U1 symmetry. Here I'm going to do it with scalars. Doesn't really matter if you choose to do it with a scalar, composite, whatever. So what you have a radial mode, a Higgs mode, and you have a Goldstone boson. And now I want to break this guy. And what I'm going to do is something a little perverse. I'm going to break the U1, but preserve a Zn symmetry of my U1. So I write a potential that is very Flavon-like, right? Where my scalar has charge 1, fermions have charge, well, have no charge, except I guess under a Z2 symmetry. And so you have to write a high dimensional operator to sort of generate a term. But you'll notice phi to the n here is a function of n over capital F, the symmetry breaking scale. And the IR person does not see the n. It only sees this combination. And in particular, the radial mode depends on, no, I didn't say it. The radial mode depends on the bev of this guy, which is some capital F. But the IR little periodicity you see is capital F over n, which is much smaller. And so the effective field strength you see is much smaller because of a discrete symmetry.
But wait, is this normalizable?
Yeah, so no. So then this is going to be a further one. So this is only one step up, but we'll hopefully. Yeah. Well, I don't know if I will actually write that down, but there are many different ways of generating. It's very Ising model-like. You can say it's flavor symmetry. There are a large number of ways to get something like that. Technical details, if you want to match what I was doing in the IR theory, you really want to take large symmetry breaking scale, large N, but keep loop expansion small, and keep lambda n squared constant, which is what actually fixes your radial mode to be a constant. And the little f I was talking about before is the full symmetry breaking scale over n. Turns out this computation will match exactly onto what we had before, basically because this scalar to a large power, if you just write it as the Higgs mode, pull out a bunch of stuff, take a large n limit here, you'll notice it exponentiates as well. So in some large n limit, the way the radial mode appears is exactly the same way as the scalar without an I, without an I. And so just do exactly the same computation as before, but add in a new source term for your radial mode, which doesn't have an I in it. So go through the exact same computation. Now there are 4 source terms. Still do the same thing. I guess you go through, have the same thing. What you get instead is what's regulating the integral is now a Bessel function instead of 1 over your distance squared. And so you get the exact same answer here, just with the Bessel function in the numerator, which does regulate everything. So it's still IR finite and still dominated at this small scale little f. In fact, at high energies, this answer is actually exactly what you expect out of conformal perturbation theory. It's just a differential running between the mass term and the Yukawa coupling squared, right? As you feed into the mass term, both of them are undergoing RG evolution, exactly what you expect. At low energies, you get the 1 over distance squared exponential as before. And there's actually some new scale here, which is basically your radial mode over the anomalous dimension. And so you can just go through and calculate it. You see, as you increase sort of the hierarchy, and as you increase n, the integral is dominated more and more in the IR. So basically, as expected, the IR cancellation is actually correct and works. Yeah, this is, at this point, I'm working towards a Z infinity symmetry. And so in some sense, this is what the calculation gives. At high energies, you get some differential running from conformal perturbation theory. It dies off. The integral is actually dominated at a scale little f here. Between that and the scale of actual new particles, you have some multiparticle final state. And then at lower energies than little f, you just see the Taylor series, you see the linear Yukawa coupling. Okay. So,
but you can take m rho to be equal, this f or divided by n, right?
Yes, that's right. So if you take the limit where m rho approaches the scale little f,
yeah,
basically none of this new stuff I talk about, you never have to resum any exponentials. Everything goes as before. Yeah.
Mm-hmm.
Okay.
This requires small Yukawa.
Yes. So technically speaking, this is really in the infinitely small Yukawa coupling limit. So for example, I don't think 1 quite qualifies to that in the standard model. So who knows if this has anything to do with reality? It's more just amusing field theory at this point.
You know, your argument reminds me of something else.
Yeah.
Like, technically, not in essence, it's very close.
Excellent.
You don't remember it, but in the 1990s, people discussed a lot instanton-induced baryon number non-observation in the standard model.
Mm-hmm.
And there, it's also generates, if you want something, generates, it grows with energy.
Yes.
Small energy, it's e to the power minus 2 pi alpha, 2 pi divided by
Yeah.
alpha, which is
This is the scalar answer.
alpha unification, scale and coupling constant. And the standard model. So you can forget. But then there were a couple of groups who noted that if you pump energy, then this grows very fast with energy.
Yeah.
And this you formally continue the energy beyond this or close to this failure on mass or beyond. You hit the unitarity limit. Interaction becomes a order of magnitude. Okay. But actually, that's not true because you forgot, interaction becomes strong itself, unitarize itself through the Renormalizable type procedure. Because this blob which you roll, blob and many lines attached, you can repeat. You can make it like a molecule. You make a chain of blobs. If they grow very fast, unitarization occurs well below the point which naively you would say you have to go in order to unitarize. You don't hit the one blob unitary limit because you have to take never. You have to take into account the whole chain of these blobs. Then the theory is unitarized at much smaller level.
Okay. Oh, interesting.
Much less than one. So it's still exponential, but it's square root of this exponential from which we start.
Okay. Interesting. Actually, if you just
I don't know. I don't know if anybody remembers, but in 60s, long before, people discuss this kind of cutoff in theory, like for Fermi interaction or gravity, in a way that similar that you write in this what they call super propagate or whatever, where kind of divergences would be summed up. And give this, and I'm talking about very old stuff. I do not think anybody besides me remembers this even.
Even I don't remember.
Right. It's what I was going to say, Misha, that it is even before you, right?
Okay. So how about, since the rest is interpretation, and I don't really, like I said before, I don't quite fully understand why the results are the way they are. So let me just conclude, since we're already a bit over time now. Think we can? Okay. Okay. So let me just say, if we take this IR theory I wrote down, and you apply the statements that people like to make, that they know where the mass of new particles coming from Cornet couplings or the mass of new particles coming from Yukawa couplings are about, and you actually draw this on the picture, what you find is these are all parametrically separated, is the mass scale where there are actually new particles, the rho meson or the Higgs of this guy, is parametrically above the scale where people say they normally expect them to be. So it's sort of, in some sense, just a straight up counterexample when people say it must be new particles because of this reasoning. However, if you just weaken it a bit and just say, actually, it's more like dimensional analysis, you don't know what's going on, you do find that there is new physics that appears before these scales. It's just the scale at which you start spitting out like 2 scalars or 3 scalars. It's different than what you would have thought or what people have said. And so I would say, at least in this case, because I gave an explicit example where the dimensional analysis question does make sense, dimensional analysis doesn't fail. People have just haven't guessed or haven't just assumed that they knew what the answer of dimensional analysis was, where it doesn't always need to be the distance to the floor. It might be your missing air resistance. It might be like, right, dimensional analysis doesn't tell you what happens. People just assumed that they knew. And why this happens, I don't know. I think the best answer I know of is the one I said earlier, which is that there's just for all Goldstone bosons, their potential are always have essential singularities as f goes to 0 because they're of their periodicity. And that means that everything has there's an essential singularity as you go into the UV as well, just by.
But at the same range you are talking about the energy of order of Earth. This interaction of phi particle is strong, right? And it could be that you have new particle there, which is made out of phi.
Yeah, so it's not true that the interaction is strong because I can take the Yukawa coupling exponentially small, right? If the Yukawa coupling was 0, it would not be strongly coupled.
No, but interaction. I see. You mean that there is no small because of y? Why it's small?
It's small because I'm going to take y epsilonically small. Epsilon could be like e to the minus 100,000 or something like that. And so even though I'm at the energy scale of order f, the theory is not strongly coupled because if y was 0, there would be no interactions. It would have no. It would be a free theory. So
I see. Okay, I agree. I agree that it's you can use it as an argument, right?
Yeah. There is one other thing that I find that's probably just me being stupid, which is I should know, right? Dimensional analysis, like looking at the spurions that come along with free scalars and things like that, will tell you how the Yukawa coupling appears. But I don't know why you don't put in any other energy scale in here, like the UV cutoff, the rho meson, or anything like that. Why in this theory is it dominated at the scale little f, which is not the scale of any new particle? I can't seem to come up with any dimensional analysis argument that says, I've given you the theory, yes, that it's finite, and it's finite at the scale f instead of the mass of a particle or anything like that. Why is this the case? I don't know, but I believe very strongly in spurion arguments, and I feel like there probably is an argument. And yeah, I just seem to be too stupid to realize it.
No, but once you assume that there is some kind of symmetry which maintains this your sine phi, then you already got rid of this UV, and then the only scale which remains is it's F, right? So then it would be only this, right?
Yeah. So I guess the thing is, I don't know why it's cut off at the scale F. Like I should have been able to tell you this without doing a calculation, right? Like I don't believe in doing calculations I don't know the answer to, and I don't know the answer to this ahead of time, and that really annoys me.
Sorry, but this point to your own logic, right? F is your new physics scale, just no new.
Yeah, but there are other new physics scales. Why is it not cut off at those other new physics scales, like new particles, the UV cutoff, any of these other things? Yeah, it could be some row.
You just want to take
No. But in your argumentation, when you sum up this kind of divergent loops, you see once you say that it suppresses UV, right? Then if you believe that UV is suppressed, then F is the only scale in the way you're doing your argumentation, right?
Yeah. And so like once you do the calculation, you see that it's cut off at F. I just don't know how to do it. How to get the answer without doing the calculation.
My assumption F is the lowest scale.
Yes.
So,
but you would think
there are many further layers of onion here. It's the lowest scale.
The answer is if you just put in any old scale here, it's dominated by the highest scale, not the lowest scale.
You talk about the naive hierarchy problem.
Well, I would just say.
You see, that's the point, that you consider, forget about y at all.
Yeah.
Put y equal to 1, it's an overall factor in your amplitude. But consider you have a local vertex with arbitrary number of legs if you expand size. Consider just iteration of this vertex.
Mhm.
two vertices emitting this phi field.
Yeah.
Okay, then this vertex will be highly singular because each expansion, I mean, each extra line,
Yes.
right?
Yep.
In 2 dimensions, as you know, this is the standard trick in the couple theory.
Yeah, this is bosonization.
Yeah, it's that you get e to the power log of some distance between them, and then it's x to some power, and x is the anomalous dimension. It can grow very fast, very fast. But here, in 4 dimensions, the green function and coordinate space of the boson field is 1 over x squared.
Instead of log.
So you get e to the power some coefficient divided by some coefficient times 1 over x squared.
Yeah.
Okay. And then we come, let's say this coefficient is m, because m is only the dimensional parameter which appears in your side there.
Yeah.
So it's e to the power 1 divided by f squared over x squared, right?
Yeah.
So it's clear
Has to
that
be,
you cannot, the point where x squared, f squared becomes order 1 or less, it's a bad point.
Yeah.
And that's defines the dangerous point where your new physics comes about. It comes about at energies of order f, because the interaction, multi-point interaction, if you have a local interaction of many scalar fields.
Yeah.
Just iteration of this interaction gives strong effects if f of what energy of order.
But if I choose the Yukawa coupling to be exponentially small, the theory is still not strongly coupled.
No, that's because you consider Yukawa coupling is small, it's an overall fact.
Yeah.
It doesn't change.
But if I took 2 blobs,
but if you explore this set of amplitudes, many amplitudes, you have a number of amplitudes. All of them are proportional to y squared, y cube, or y to the. You still will see, for given y, if you make measurements, let's say you normalize all your calculation by dividing all measurements by dividing, let's say, by y squared. You will see their new physics at the scale f.
Yes.
Because it's new physics of many scalars.
Yeah, that's right.
So that's what you are telling us.
Yes.
No, but look, along similar line, let's say you are doing this calculation by dimensional reduction. Sorry, by dimensional. Yeah. So let's say that you are starting from renormalizable version. So your dimension is less than 2. Okay. Start from dimension less than 2. Then it's renormalizable theory, right?
Yeah.
Okay, and then your summation of 1 over x squared correspond that at d equal 2 you will have logarithmic corrections, right? In the way you're calculating. And I think that this summation of 1 over x squared could be translated into what's going on in summation of log at d equal 2. You see what I mean? That in this sense, it would be similar to kind of anomalous dimension of what you're calculating, right? Because at dimension 2, it is normal logs. And I think that this kind of suppression later, it's kind of could be, it's just a guess. That it could be, you can try to relate it to what's going on when you're crossing d equal 2.
Yeah. It might be possible because like this Yukawa coupling is sort of like your 2D sine Gordon theory with 2 fermions.
Right.
And then you bosonize one of them, but not the other one.
Yeah, right. But it's what I have in mind, right? That you can start from, and if you're doing dimensional regularization, that it's starting from d less than 2, it's the only way.
Yeah.
You
Okay.
see, if you, for instance, are interested in Y square effect, but in the amplitudes two fermions into two fermions,
Mhm.
you don't get Y square.
Yes.
You get much exponentially more of an effect due to a large number of bosonic lines.
Mhm.
All of them, because this vertex has Y only once, but it is half F, 1 over F many times.
Yeah.
And the result would be exponential.
Mhm.
So therefore, exploring very carefully two fermion into two fermion amplitude, forward or not necessarily, but it may be even close to forward
Yeah.
scattering, you will immediately see that new physics comes at energy equal to F.
Yeah. I think that's right.
So you just chose your spectrometer in the wrong way because you are trying to find the effect of new scale in the phi propagator or effective Lagrangian. Okay, it's not sense or poorly sensitive to it, but you can take a different amplitude, which is much more sensitive to it. Of course, it will still be suppressed by Y. But Y doesn't change, with energy or whatever, it doesn't change. So you have to understand that there, in your physics, in your imaginary model, there are effects which are suppressed by Y. But if you start looking at this level, you will immediately see the new scale. That there is a new scale coming up there.
Yeah. I think that makes sense.
So that Y is small, therefore, if you have a theory with Higgs effect, for instance, your masses are very small, right? But interaction of two Higgs will be much more intense.
Yeah.
So it's a more tricky situation.
That's actually even one of the things I'm thinking is how to extend this to non-abelian, because doing anything like this non-abelian like the Higgs, I have no idea how to do. It's very.
No, I can tell you, look into, because it's a non-abelian case, it's directly related. Very number conservation processes at large. Is there a way to find a new scale there? You know that at zero energies, the scale is e to the power minus 4 pi over alpha.
Yeah.
But if you go to high energies, you can find that you can strongly enhance this effect. And there is in the spectrum, there is also a signature to that. There is a spheruron, which is quasi-stable soliton. It decays. But okay, it's a resonance. We can look for a resonance and we will see a new scale in this phenomenon where in this where two phenomena come. And it's the scale much higher than the scale of the W.
Probably that.
But it's the scale around. What is it around? Arkady, do you remember? Is it around the unitary limit or below it?
You mean the scale of this?
Spherical mass. It's a water V divided by.
No, spherical mass is like a monopole mass, similar.
Like what?
Like monopole, MW divided by G square.
V divided MW divided by alpha.
Yeah, right.
Or V divided.
Yeah, you can rewrite it in V divided by G, right?
Oh.
V over G,
No,
M over
MW
alpha.
is V times G. Alpha is G squared. So in terms of
M over alpha, V over G.
V over G. So in principle, if you do these measurements at this energy, you collide just the quarks, which a number of quarks with a lepton, and looking for an outcome with no lepton, for instance, P minus L conservation, you will find this phenomenon in this scale. Because there is no new phenomenon without its scale. And if there is a new scale, you will always find it. You just have to look where to think where to look.
Find it better.
Yeah, because this phenomenon has no impact on, let's say, if you look for the mass of the Higgs particle, you will hardly see it. It's exponentially small. But if you choose your detector in a proper way, you will see this new scale.
Yeah. Okay. Can you give us your final words?
Final words is when people say that whatever new naturalness or whatever says new particles have to be there at 500 GeV. Here's an example where it's not new particles. It's instead just new phenomenon of a different sort, in which case where you might have to look for multiple Higgses in a final state or things like that. Somewhat amusingly, in this example, you actually get the mass of your scalar and the mass of the fermion to be related by a square root of 2, which is actually amusingly true in the standard model example. I don't know why, but it's just amusing if nothing else. But of course, it may not have anything to do with the real world, because to do any calculation, I really needed exponentially small Yukawa couplings. Maybe y of 1 rather than 4 pi is small, but I highly doubt it. Yeah. All right. Thanks.
Yeah.
Thank you, Anson, and we can continue our discussion. You'll be here today, and also if you want to join dinner, let me know. It's a very nice talk, and we can keep on discussing here. But I just want to let some people with other tasks who need to leave, you can leave. Okay. Thanks. Yeah.
Give us some time for lunch.
Yeah, indeed.
Yes.
Indeed. We are grabbing lunch and come back to the coffee area. Yes. Akari, thanks.
Yes, it's very
Yeah,
nice
but,
seeing you again, even though it's over Zoom.
Okay, but look, I think that something wrong with, kind of, I cannot see anybody. It should be camera which shows, what's going on, because you can see me, but I could not see you.
Yes, I should have realized that when they were setting things up. Sorry.
No, but okay. No, it's still easy when you still can have an extra camera looking, right? Besides the presentation, right? So maybe next time. Okay, thank you.
Yeah. All right. Thanks for coming.
Yeah. Bye.
Yep.
Okay. Now you can see. I can see you.
Yes.
Okay.
All right.
Yeah. Hi, Akari. Good to see you.
Hi, Arkady. Nice to see you, Arkady.
Yeah. I think that you are not sincere. It's not good to see me.
You're looking good, Arkady. Looking good.
Okay,
if you
thanks.
really thought it was so nice to see him, you'd be in KITP playing tennis with him.
Exactly. Oh, I wish I was playing tennis with Arkady. Yeah.
Sure. Right. Okay, next time.
Thanks,
Bye.
Arkady. See you.
Thanks for the talk, by the way, and so.
So we're just grabbing for the back.